So this week we're going to move into chapter 6 of your textbook, and we are going to talk about different types of number systems. So we are very familiar with a base 10 number system because that's what we pretty much use across the board. It's a Hindu-Arabic derived number system. That's where it kind of originated. And we use base 10. Most people think we use base 10 because it's the simplest, but in reality, it's probably just we think it's simpler because we're more familiar with it, right? It's what we're used to, and it is what most of the current modern world uses. However, in normal day-to-day activity, there are applications of different number systems, and you'll see some of those this week as you work through the material. The Babylonians, for example, used a base 60 number system, which looks completely different from ours. And so we are going to talk about how to convert back and forth between different number systems, and then how to do arithmetic with those. So when we say that our number system is base 10, that's because our place values are multiples of 10. So for example, the ones place is 10 to the 0, right? Anything to the 0 power is 1. So 10 to the 0 power, it gives us our ones place. 10 to the first power gives us our tens place. 10 to the second power is 100, gives us our hundreds place. And we can do that on up as high as we would like. So that's what we mean by base 10. That means that every place value is a multiple of 10. So the Babylonians actually used a base 60 number system. So what that meant was that every place value in their number system was a multiple of 60. Their first place value was 60 to the 0. Their second was 60 to the 1, 60 to the 2, and so forth. Just as a note, I don't think we get to decimals in these sections, but negative exponents is what gives you our decimal system. So the tenths place, the first place after the decimal, would be 10 to the negative 1, 10 to the negative 2, 10 to the negative 3 if you want to get smaller numbers. Positive exponents give you the bigger numbers. Negative exponents give you the smaller numbers. Okay. So in these two sections, it's 6.3 and 6.4, you are going to see some new notation. In that notation, you're going to see a number and then a subscript. The subscript indicates the base that you will be working in. So we normally don't write a subscript because we all understand that we're working in base 10. But in this lesson, where we're introducing other bases, we would actually need to put a 10 subscript on our number to say, hey, this 18 is a base 10 number. Or we could have 18 base 3. So 18 base 10 and 18 base 3 do not represent the same thing. So you also need to think about when you're working through this lesson, you're going to have to make a distinction between numbers and numerals, right? So numbers are what represents a quantity. To us, when we say the number 2, we mean 1, 2. We mean the quantity 2. It represents two actual things. We have chosen to use a symbol, right? That, I can't draw it on the screen, but you know what 2 looks like. If I write 2 on the board, you know what that means. That's just a made-up symbol to represent that quantity. So in this lesson, if you use the symbol 2 in base 3, that does not represent the same quantity. It represents a new thing, and you're going to learn how to convert between bases. Like if you see number 2, base 3, you're going to learn how to convert that to base 10 so you know what it represents. So just keep in mind that the symbols that we use to represent numbers are just that, they're symbols, and they can be changed. We can redefine them. We can say now this symbol that we call 2 is going to represent something different in base 4 or base 5. Okay? So again, you're going to learn how to convert back and forth between systems. So for example, if you ever wanted to study Babylonian culture, you would need to understand what their base 60 number system is. That would be easier for you to do if you could convert it to base 10, what you're familiar with, and then look at it there. So we're going to practice doing that. Another application that uses a different base system is computer programming. So computers almost exclusively deal in a binary system, right? Just 2, they have 2 things. So we can convert numbers to base 2 which is a binary system and what computer programming uses. So that's another useful application. Also, you will see another notation used. So we have 10 symbols, 10 numerals, right, that represent quantities, 0 through 9. And that's because we're a base 10 system. Once we hit something bigger than 9, we go to our next place value because we have a 10 system. Well, say you're working in base 13. You wouldn't go to the next place value until you hit the 13th digit, right? So that means that for when you're using base systems that are bigger than 10, you need more numerals, more symbols. So our textbook chooses to introduce letters. So for example, if you're working in base 13, you would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, right? We're going to introduce 2 new symbols. And again, those are just symbols. They can mean whatever the system needs them to be. They are just the written symbol for what we're doing. Okay. So once you, in 6.3, so you have 2 lessons. 6.3 is just going to have you convert back and forth between different systems. How do you go from base 13 to base 10, from base 10 to base 4, and you're going to practice that, okay? So once you have a pretty good grasp on converting numbers back and forth, you are going to go to 6.4, and there you are going to learn how to do arithmetic in different base systems, okay? Back up, when you're converting, you're going to learn like longhand how to convert, and then at the end of the section, they're going to teach you a shorthand method for conversion. It's called the dibble-dabble method, or the double-dabble method. So just that's what that method means. It's at the end of 6.3, and it's a shorthand way to convert. You can always use the longhand way if you understand that. You'll get the same answer. So a tip when we get to adding, subtracting, multiplying, and dividing. 6.4 is going to teach you the steps to do that with your different base systems. So it's very similar to when you learned arithmetic in early elementary school, right? You learned to add your tens, and when you added your ones, if you got something bigger than 9, then you had to carry a number. You're going to do the same thing in different bases, right? Think elementary math, but imagine that you're learning elementary math with more digits. So maybe if you're in base 13, you won't actually carry, right, until you get bigger than 13. If you hit 14 or 15 or 16, and what you're going to be carrying is letters, because 13 is going to be represented by, or 12 is going to be represented by A. Your textbook is going to walk you through all the steps, and I'll be happy to answer questions and work examples for you either online or in our class. One tip, though, that is useful, if you're really good at converting from bases to base 10, you can always convert your problem, your addition, your subtraction, your multiplication, or your division problem. If you convert properly, you can convert to base 10, add, subtract, multiply, and divide the way you have all of your life, hopefully, and then convert your answer back to your base, right? So you can do all of your arithmetic in base 10. You would just have to convert twice. You would convert to base 10 to do arithmetic, and then back to the original base for your answer. You'll get the exact same thing. So that's just a note. The textbook's going to show you how to keep everything in the same base, do all your arithmetic like start to finish in whatever base you're using, but you can always do the conversion and just add, subtract, multiply, and divide in base 10 to get the same thing. So let me know if you have questions.